Okay. So I'll start in a minute. Actually, I don't know why I even started the stream that early. Uh, Maybe I'll go back and think. We'll just so we won't be here on Friday. So, and if y'all got, I don't know, like if you got a test after this, you could lobby them or lobby the class to not have it. Maybe you can go home early. I don't know. I guess I could go ahead. Should I go ahead? Actually, for some reason, I think it went ahead because I don't think I was there. I think I was right there. So if you don't mind, I'll just go ahead. I mean, so the way he starts in 3 dimensions is the same way he does in two, except of course there's an extra dimension. So guess what? He has the same pictures, but now they're 3D pictures. And so if you got a cable, you can only pull on a cable. If you've got a flat surface here, you can only go normal. So this vector is normal to that flat surface. Same thing here. If you've got a ball and socket joint, you can actually pull up or either direction. That should keep it fixed. This is a now this is a this part is one of those things that is very nebulous, and we'll come back to this because there's some problems in his problem set related to this one that really bother me, and we'll talk about those in a little bit. So this, if you shove this pipe here, it should just shove right out, and if you twist it like so, it should have no resistance to that. So that's why you don't see a value here and you don't see a rotation there. So essentially, you can torque this thing or pull here and pull here. It'll resist it with this. You can pull down and pull up. It'll resist it with this. And for that matter, you can pretty much do everything except those two forces. Now, I'll kind of go back to this one because you got to read between the lines because sometimes he's telling you this and then he reneges on it in a few of the problems. So here's one in which you can't see this picture very well, but it's a square shaft. In other words, and I'm not exactly sure why you would want to build one, but you could twist it and it'll resist. And then a thrust bearing is a bearing that I don't know if you've ever seen these. There are Timke sells them. I think that's the way they're. Okay, so you imagine. Okay, this is a roller bearing. So this is like a pencil, and then you get another pencil over here, and then you build this. I'm not a great drawer. You know what? Let's do this. I think I could find that and show you that. My drawings are so they're called tapered bearings. Let's see if I can find one. Um, okay, so they're much better. They're much better drawings here than what I can do. Okay, so like thing about these things, this is a good one because it shows the internal seat right here and the external seat. So if you put this bearing and put a shaft on it and you shove from left or shoved this way, here, let me just, maybe I can get a better, because if this is, oh, well, this is going to here. I didn't mean to go do this, but what the heck. So if you go in and, oh, I don't even have any, that started. I have no idea what that is, but here. Oh, that was for fluid. Okay, now put it down here. Okay, put it down here. So in other words, if you put a shaft on this thing, and you shove on that shaft this way. This is inside of a cylinder, say. Ooh, that's not a very good. So this is seated in a cylinder, and an axle goes through here, and pretty bad drawing. And so you got this rod like this. You shove this thing, it's going to push this bearing against this seat, and it's going to resist. But if you shove it this way, guess what? This thing falls right out. So what you do is you take two of these and you stack them in a, so you take your, say you have an axle and you want it to be supported. Okay, again, I'm not a great drawer. It's sitting in a sleeve, and you put a tapered bearing like this on it, and then you put a tapered bearing like that. And one will take the force one way, and the other one will take the force the other way. So these are the tapered parts. So if you push it against this way, one of these bearings is resisting, and the other is just floating. And you do the other. So that's how you put an axle and a wheel on it. So when you're turning left or right, the wheel doesn't fly off, you know. You can do the other way where you can put ball bearings. The problem with ball bearings in this, and there's a lot of cars that have this in them. So you'll have these ball bearings in the internal. I'm not a great drawer. The internal thing sits like this. So here's the thing spinning, and here's what's holding it. As you move left and right, you're pushing the balls on either side, and it will generally tend to wear out quicker than those. But if you don't care and you want you want them to come into the shop because that's how you make money, then you don't use taper bearings, which is sad. But so anyway, so this is single thrust bearing. Well, okay, there's more to it than that, because you could have a tapered bearing that way, won't take a load this way, but will take a load that way. But if you took two tapered bearings in there, it'll take a load either way. So there's more detail here, and this is the one again that annoys me, but we'll come back to that. A single pin is a 2D pin. You cannot have a 3D pin. If you've got a 3D pin, it's a ball in a socket like your arm. If it's a pin, regular pin, then that means if I push this over to the side and take a moment, this thing will give you a moment back. A ball joint, like your shoulder, if you don't tense your muscles up, it just moves anywhere. So now single hinge, this is in all sorts of doors. It doesn't take a moment across here. It basically opens and closes. And then you got the fixed support. It takes everything. It's just like a mailbox welded to the ground or dug in the ground. These are rare, the ball joints, but they do exist. Journal bearings. And then you've got the single pin. This is pretty common on all sorts of hydraulic. And this I can't even see. I mean, I'm taking his word for it. There's a thrust bearing in there. But then again, there's more detail there. Does it thrust both ways? Or I don't know what you would want to have a bearing that wouldn't thrust both ways. Okay, so this is this may be one of the parts that really bother me. Okay, so he says, consider the rod and the plate acting along the associated free body diagram, da-da-da. Then he says, he doesn't really use much in words, except he says this. When you look at it, you have a bearing, right? Okay, so technically, this thing can take a moment like so, and it can take a moment like so. If this is truly a bearing, unless it's allowed to rotate all sorts of ways. So to me, I'm like, hey, wait a minute. You've told me that this is a bearing. So he says, properly aligned journal bearings A, B, C. What does that mean? He shows no moments here. He shows no moments here and shows no moments there. But in fact, it's possible for them to take a moment unless they are floating. And you can have floating bearings, but even if you did put a ball bearing and put a shaft through it, go up to it and take it and try to do like this to it, and it will resist your motion. So if you put a bearing, doesn't matter whether it's properly aligned or not. It can be perfectly aligned, and you can look at it, but if you do like this, it's going to resist you, and you do like that, it's going to resist you. So in fact, it bugs me that there are no moments placed here. The reason I think he puts no moments there is because he can't solve the problem with those. It's statically indeterminate otherwise. So he goes through and solves that somehow, but that's, to me, I don't like that. Okay, so this one's kind of straightforward. It's got a pin through it. He did put the moment here, and he did put the moment here. So whenever you see these journals, these bearings like here, the first thing I would say is, hey, wait. So that's one of the things I don't like about the things that are presented here. Plus, there's something weird there. Look at that. Is that a 2 or a 5? I see a 2, but I also see a 5. See, I see a 5 right there. So which one is it? Is it 2? But it's definitely 1 and 4. What chapter is this? Can't be 2. It's got to be 5. Yeah, so somehow there's a mess up there. Okay, so what is this? A properly aligned journal bearing at A and at hinge C. Now the hinge C, I'll buy into that. But wait a minute. So the hinge bearing, it can take a load like this. I mean, a moment. And it can take one across here. It can't take one across the other. So he simplified this to the point where he makes it a solvable problem. Now, what he should do is he should say, with minimal moment there, or neglect the moment there. You don't really talk about properly aligned, because you can properly align something that doesn't really help you. So, what do you get on these? Well, you do the same thing. Some of the forces and some of the moments. However, you got 3 of them, and you got 3 of these. So before, in 2D, you had some of the forces in the X, some of the forces in the Y, and some of the moments, which means I can have 3 unknowns. But here now I can have 6 unknowns. And that makes the problem a little bigger. Okay, then he starts talking about, okay, so his constraints and static determinacy, that's where you come into play here. So what does that mean? That means you have, in a 2D case, you have 4 or more unknowns. It means you cannot determine it with statics. If you have more than 6 unknowns, you can't determine it with statics. Let's go back to that first case. How many unknowns does he have here? Whoops, hang on. How many unknowns does he have? Not too surprising. He went in and he has 1, 2, 3, 4, 5, 6. If he had thrown a moment in here, just any moment, you can't determine it. Too many unknowns. So what he's done here is he said, okay, I can't solve this particular way. So what I'll do is I'll make it so that I'll just assume that to 0. That's a scary thing to start doing. So to me, I don't like that. This one seems to be okay to me. This one, not so much okay. Here you got 1, 2, 3, 4, 5, 6 unknowns. However, a bearing can take a moment, and this can take a moment across this axis and this axis. So you got, actually, you can take 2 moments here. So you can have 1, 2, 3, at least 3 more unknowns. This one's okay. And this one legally is statically indeterminate unless you assume away the moment. So when you're working a problem in a textbook, follow the textbook. But then when you get into real life, be really careful about this, because there are times that problems crop up like this, and I've seen people assume away a force or a moment, and if you're not careful, you can end up in a world of hurt there, and actually things can start breaking on you. So what is static determinacy? Constraints means, in a way, well, I'll just take static determinacy. You can determine it because in 2D you had 3 unknowns or less. In 2D you had 3 unknowns or less. In 3D you had 6 unknowns or less. If you had more, you can't determine. So that's static determinant. That is statically indeterminate is what's usually talked about. So, for example, you look at this thing. Hang on. Wait a minute. Okay. So this is a 2D problem. So you got 1, you got 2, you got 3, you got 4, you got 5 unknowns. 5 unknowns. In 2D, you got 3 equations. You can't figure this out with just statics. If you're in mechanics of materials, believe it or not, you can. So, and why? Because when you get in mechanics of materials, there are extra equations that show up. So this one, okay, how many have you got? This is a 3D problem. 1, 2, 3, 4, 5, 6, 7, 8. 8's too high. It's greater than 6. No, you can't determine that. So here, I just saw this word. It says, involve the physical properties of the body, which your scissors dealing with it. Mechanics of deformation, such that mechanics of materials. This is how you can take it from 6 unknowns up past it. And at that point, you can solve these things. But that's next semester or whatever semester it is. Oh, he puts a little asterisk. Oh, see my book. So there are possibility of putting improper constraints. Here's an improper constraint. Take a look at that. See, what do you think could happen there? Physically. A little ball bearing here. You push on it, and the thing is just going to flop. So it's improper in the sense that engineering improper. It's basically stupid, but you can do this, but you're not going to get what you think out of it. Here's another one where you put a ball joint here, and you push it there. The thing is just going to swing down and be straight vertical until maybe this member hits the edge of the support there, maybe. So that's what he's talking about, improper. Here's another one. It doesn't seem improper until you realize there's actually a component of force pushing to the right. And so it'll just keep rolling that way till these rollers fall off. And then, where are you then? Now this one, okay. So this one may seem improper, and from a static viewpoint, it is. But this one's not as bad as the ones above, because what will happen is this member will move off and probably change its orientation so that it'll do that to the point where it'll force itself into a position in which equilibrium can be satisfied. So if that makes sense, you push it this way, the rope is going to stay the same length, but it's going to move that way. Probably this one's going to move a little bit that way, and this one's probably going to move a little bit that way. so that the tensions offset this force, and you'll end up with sum of all the forces equals 0, and sum of all the moments will equal 0 as well. So it will force itself into that. So this one's a little bit different. You can do this, but don't expect it to stay vertical. This one's a little bit silly as well. And this one is physically doable, just like the one above. And what would happen is it would pop down like so, to the point where, if you think about it, this force, this would have a component in this direction, this would have a component in this direction, would offset the component going down. But it will drop to the point it stretches. Okay, if it stretches, then you're in mechanics of material. So that's statically indeterminate. With mechanics of materials, it's easily determinable. And physically will actually happen. These are just plain dumb. I mean, there are dumb ones. And then there are things like this that, it behaves in a little bit different way than it's drawn, but it will behave okay. And so you start looking at these, like this is a weird looking one. I can't even tell. I think these are little balls on the bottom. So he's got these little balls here, but obviously this one is not. This one looks like a ball joint because it's got components that way. So the first thing we look at is being able to take the physical into a free body diagram. Now in this section, it's probably pretty important to do that because then you can immediately identify 1, 2, 3, 4, 5. Yes, and 5 is less than 6, so I am okay. I can solve this one. However, if I made this like welded or something, or a joint that had this would be a Y and say a X, suddenly I'd have 5, 6, and 7, and I'm gone. And I can't solve it. So many times in these, in 3 dimensions, physical items that you're going to make are not statically determinable. And therefore, mechanics of materials become very important to you after this, when you go into the real world. So you look at this thing, first thing he does is he sums the forces in the X. Okay. Sum the force in the X. You get this one all by itself, and it's equal to 0. That simplifies it. But if I had an AX out here, then I would have a relationship between AX and BX. But I don't. And then the Y tells you that. Now, you think about it. So I've got rid of the X, got rid of the Y. Now I've got 1, 2, 3 left. And so I've got one equation here in which basically the 3 of them end up in. So that's not enough. So now I'm going off into the moments. And so you just have to pick yourself a spot. He looks like, to me, he likes this corner right here. But you can do it anywhere. And he sums the moment about the X. And so what he's doing is this 981. So he's summing about the X. So imagine what you're doing. Here, let me get rid of this. Hang on. Okay. So you're summing moments. Imagine with your hand here, you're summing moments. This will produce one that spins about that axis. 981 times 1. This one will produce one that spins about the x-axis, and it's TC times 1, 2, so it's TC times 2 the other way. And so we'll just take this to be positive. And so this one will be negative. Then you get a BZ and a 2. 2 comes BZ. And then okay, so I got the 981. This won't produce a moment because it's going right through that axis. That is only about the Y. So as far as I can tell, that's all I've got is those 3. And if I look down here, I get those 3. That one. Oh, where's the 300? 300. Oh, he's doing it about prime. Where's the Y prime? Oh, okay. Sorry, he's doing it about this line. So we're doing it about different lines. He did it about that line probably to eliminate this force and this force because they don't produce a moment about here. So this offsets the moment produced by these two. So that's how he ends up being able to solve for AZ right off. Then the Y prime, he's deciding to do it about the Y prime. So he does it about the Y prime, about this axis. So there should be the 980, the 300, the 200, and then the TC. And so the 980, 300, 200, and then the TC. And from that, he gets the remainder of the 3. So let's see what he did with this one. Okay, so this is another one that's very annoying. But I'm not trying to be bad or anything, but if I were working in the field and someone's told me that is a bearing, I'm going to put the moment here and the moment across here. I just can't see it not being able to withstand a moment. In other words, if I went in here and pushed on this, is this, and this was not connected, is this going to take a resistant moment? Yeah, it is. So technically, why is he doing that? Well, because he says 1, 2, 3, 4, 5, and a 6. But if I put the 2 moments in there, I get 7 and 8, meaning it's not determinable. So this one is a mere approximation, and it needs information from mechanics of material. So you just need to be aware of that when you're looking at these in the field, that you need to ask the question, really, if I put a bearing in there, if that bearing is really thin, I don't know the definition of thin, but say a thin piece like this and the rod goes through here and that rod could move in that bearing kind of freely. I wouldn't imagine it being able to do that because that just doesn't make sense. Because if you're doing that, it's a small support, you're not going to be able to support much weight. So in my mind, if you're putting a bearing to support a lot of weight, you're going to want to put that. So then the question is it actually a bearing? Or because if you do this on top, yeah, you can twist this thing and it's going to offset that. But you just need to be aware of that. He has taken this and unduly simplified it. But now that he's done that, you look at this and how could you do this? Well, some of the forces in the Z will tell you that 900's got to be offset by this and this and this put together. Now, you can do something like this. If you sum the moments about this, you realize none of these produce moments. And you'll realize this is 0.4 and this is 0.6 out. So 0.4 times 900 divided by 0.6 is going to tell you the actual FC. And we'll just, if this thing works, earlier it wasn't working quite right. So if you look at that thing, it says that's 600. So let's go down and see, is it 600? Yeah. So you can determine that one straight off. So a lot of times it's good to kind of step back and look at your moments first, because then you can figure out stuff pretty easily. Another thing, if I go back and say, I want to take the moments about here, this way. Now I know this is 600. And now I've got this BZ. So let's think about that. And so I got 600 going this way. So I will make this become positive. So 600 times 0.4, 0.4, 0.4. I think that's 1.2. That's the moment that's produced around this axis that way. Then I got 900 going the other way. Minus 900, moment arm of 0.4. And the only other force is this one across this way. And that is a positive BZ times 0.8. So to me, I would see right off BZ is equal to, I'm going to see if I can make this figure it out. 1.2. Oh, well, let's do it. Okay, so I'm doing it that way. I'll make it 900.4 minus 600, 1.2. Ooh, this is not going to work out very well. Let me just, because the picture's not going to be able to take that. So let me do this by hand. So if you do that, and of course it's always touchy when I'm doing it by hand. 900 times 0.4, that's 360, minus 600 times 1.2. Oh, wow, I get BZ of 0. That doesn't make sense. Okay, wait a minute. Let's look at this again. 600 going up times 1.2. 900 going down 0.4. So 600 times 1.2. Oh, sorry. My math mistake. It was minus 360. So sorry. 360 divided by 0.8. 450. This BZ 450. And in fact, it's 450. So now what other moment can I do to find an answer? Well, I can do moments about anywhere. Let's just take this line right here. And I'm going to do moments this way being positive. So now I got 600 and 900, both 0.4 across. So 600 plus 900 times 0.4. And this AZ is going to be 0.8. Okay, wait a minute. 900, okay, 900, did I do that right? Plus 600 times 0.4 divided by 0.8, 750. So I get AZ equaling to 750. Is that what he's got right here? AZ is 750. So you can see I can go through this without ever summing a force. I can take a line and just go through. Okay, so I got 750 here. Okay, what did I get here? I got 450, but it was going this way. So what else can I do? Well, what other line can I do? I got that one. Now let's find BX. Let's take this vertical line, and I'm going to sum the moments this way around that line. BX has got to be 0. Okay, where's BX? BX got to be 0. Why is that? Because I look at any other thing. Okay, this is supposed to create a moment around that. I don't have any other force. that is creating that. So that's actually gone. How can I find the moment associated with AY and AX? This will be fun. What is AX? Well, I can just take any line. Just take a vertical line here. AX is going to create that moment at that line. If this were not 0, it would create one. But since it's 0, this has got to be 0. So AX is 0. AX is 0. And you notice I haven't done some forces yet at all. Okay, so that's 0. AY. Well, now I can do some forces in this Y direction. And I pretty much realized AY has got to be 0. So AY is gone as well. AY is gone as well. So you can solve these things rather. Oh, I didn't do AZ, did I? So I can do AZ by simply. No, I did do AC. Yeah, I did. It was 750. So I can do a lot of these without ever summing the forces. I can just pick different lines or locations to sum about, then sum the moments about this. You know, I can just pick a line in there and sum the moments about that line. Okay, so this comes back. These come back to this is the particular problem in which it comes back to these normal vectors. That's an interesting kind of setup there. Is he saying that that rope goes through that, or is it attached to that? It's got to be separate. Yeah, he's got them separate, so they're all separate. Okay. Okay, so to me, the way I would solve this one is similar to what he's doing, but I would recognize it's, I got enough time to kind of sort of pick this one apart. It's going to pick up part of that page that, you know, has nothing to do with anything. Okay. So in my case, what I would do is I would create the unit normal or unit vector in that direction. Okay, so in this case, it's minus k. In this case, that vector, unit vector, is going to be going minus, this is the y, let me move that over, minus 6. So I'm going to go back 6, I'm going to go up and then over. Go back 6j. I'm going to go back to I, and I'm going to go up 3k. And then I'm going to take it, and the unit vector is 2 squared plus 6 squared plus 3 squared. So in other words, this is the vector that takes me from A and goes back to C. Okay, so if I do this same thing on that vector, this would be unit vector. I'll call this C, W, and I'll call this one B. The unit vector going back to B from the ring there, or whatever A is, would be, let's see, this time I'm going plus 2I minus 6j plus 3k. Square root of 2 squared plus 6 squared plus 3 squared. So that vector, you go back 6, you go out 2, and then you go up 3. And that's how you get that vector. So this is the unit vector there. So the so now my approach is kind of a little bit different than what theirs is. I go in and I set up this. Hang on, I'm gonna wait for this to open. All right, so let's see. Okay, so I don't know which one to do, so I'll say RC first. The RC is going to be -2. It's going to be -6. And it's going to be 3. And there's that vector. So unit vector C is going to be RC divided by the norm of RC. I'm kind of apprehensive to write this, but I'll go ahead and do this. I'll tell you what, I'll even do it this way here. Here's what we'll do. Do a copy. And I'll just do a paste there. And I'll zoom in on it. And you know what I think I can do? I think I can do this. Can I type in there? I can. Look at that. This will be J plus that. This will be I. So that is the vector right there. That is this vector. Not too interestingly surprising because this one is going to be, but I mean, I can write it down, but I think I'd like to just, oops, wrong button. I'd like to just go ahead and do it. This one ends up with a plus, and this one is a B. And so now B, 3, and a B. Oh, where did it go? That's different. Okay. So here's this, and it's that one. I don't know what it's doing. This one is I, and J plus, and then K. But I think the key here is kind of this, is that if I set these up, okay, so I'm going to call this F. Hello. Okay. FC and FB. Then basically, I'm going to have FB plus FC, the vector, plus the weight equals 0. Sum of all the forces equal nothing. So what I'm going to end up with is this vector minus 0.28571 minus 0.85714. I'm copying this straight down. So it will be UC and 0.42857. Then I'm going to copy the UB from over here, and it is 0.28571 minus 0.85714, 42857. And then I'll copy this one, which is 0, 0, and -1, and it is U weight. And I believe he told us, I think. Okay, I don't know what the weight was. Now, I did forget the one that was out this direction. Okay, so hang on. I'm going to take this one. This will be, what do I do it the way I'm doing here? I'm going to take this one. This one will be the unit vector O. that one is just simply minus j. And the unit vector O minus 1. Now, what you got is FC, FB, the weight, and FO. And that's all has to be 0. So what I'll do is I recognize that weight is an actual value, which is whatever that value is. 75. So it is 75. So that's going to be 75. It's going to multiply times this, and I'll move it to the other side, and I'll get a matrix which looks like this. Let's see if I can just copy this. Here, copy, and I'll just put it right there. And then I'm going to get the 0, minus 1, 0. And then I'm going to get FC, FB, F0 equals to, take the 75 and put it, and you get 75 over here, because 75 times this is nothing, times this is nothing, by this is minus 75. It gets moved to the other side. And that's going to be the equation. So in this is UC, this is UB, and this is U0. What we should find out is the 0 might probably going to switch its direction and be negative. So if I do this, let's say, okay, so what I want to do is I want to make a matrix which is K, which will exist. Here's what I'll do. I'll do a UO and call it 0, minus 1, 0. Now I'm going to make a matrix K, which will consist of U, I believe C, UC, oh, I got to transpose that, UC, UB transpose, and then U0 transpose. And I should get the matrix out. So there's my matrix. My right hand side is going to be 0, 0, 75. So then I do inverse of K times right hand side, and I get 87.5, 87.5. That's going to be, again, FB, 87.5. And the FO, I believe, was minus 150. Minus meaning it's in the opposite direction of the unit vector I drew. So let's see what he ended up with. That's not the one. Okay. He kind of, I should have paid attention. That would have been a 7. That would have been easy to do. Oh, now he's doing something that's interesting. That's funny. So we get the 87.5. That is hilarious. So he has done the sum of the moments. That's funny, because when you do the sum of the moments right here, the force that comes down this rod has no effect, has no moment. Did he ever solve? He never solved for the force in the rod. But that's an interesting, I didn't think about doing that. So you do the cross product of that, which I think that actually is more work. So I think we'll just call it good. There's some problem sets. I think there's one problem from this. We'll just go from here. So Friday, you don't have to come. You can just, if you don't have a test,